I think that's fine. It's not minus there, is it? No. No, this is all right. Okay. So this is the next problem. The next binomial expansion problem. Again, all of these are IBAA higher level, but they might be helpful to you if you're doing something else. I'm just going to answer them basically. I've not seen them before. I might get them wrong, but if I get them wrong, you won't be seeing this. So there you go. So in the expansion, x times 2x plus 1 to the power of n, the coefficient of the term x to the power of 3 is 20n. N is an integer. Interesting. Find n. Okay, so this gives me some confidence. The last problem, we got 20 over 7, which felt wrong. But this one says it's an integer. It didn't say that before. So that's encouraging, I suppose. Out of the expansion, we're interested in the coefficient of the term x to the power of 3. We're told that's 20n. So probably the way this works is we're going to expand this, and then we're going to find that we get something other than 20n, and we can make them equal to each other. I'm noticing that it's x times 2x plus 1n. What that means to me is the term we're interested in out of this expansion is actually the x squared term, because then we're going to multiply it by x, and it's going to give us a higher power. So I guess I'm only really interested in that x squared term, which for us, luckily, is going to happen when 2x is raised to the power of 2, which means 1 is going to be raised to the power of n minus 2. Now, I don't know what n is, but the core thing with any kind of binomial expansion is the powers on each of these terms always add up to n. So I know 2x has to be raised to the power of 2, and that means this must be n minus 1. Doesn't end up mattering anyway, because 1 to any power is just itself. We do need a binomial coefficient, so this is going to be n choose 2. And then at the end, we multiply by x, because that's the term that's here. So this part is our standard formula for a term in a binomial expansion. We're just using that. And then we'll multiply it by x, because that will give us our x to the power of 3. So if we simplify this a little bit, we have n choose 2, 4x squared, well, times x. So I'm just going to incorporate that in. That's going to be x to the power of 3, which is great. Now, the part of this that's slightly tricky is figuring out how to represent n choose 2 when we don't actually know what n is. And for this, we can't really use our calculators. We have to use our formula for what n choose 2 is, which is n factorial 2 factorial n minus 2 factorial. So again, the number on the top is always going to be the sum of the two numbers on the bottom, and one of these on the bottom, I mean, well, both of them are going to correspond to our powers, but you sort of pick a power, make it the choose, and then they add up at the bottom. It doesn't actually matter which power you pick, because, like, if you've got, provided they add up to the n value, they're going to end up being the same. Like, if you've got, for example, x plus 1 to the power of 5, 5 choose 2, and 5 choose 3 are identical. Like, they're the same always. So it doesn't matter which power you're using, because you would have, you know, a term that's x to the power of 2 and then 1 to the power of 3, and whether you choose to put 5 choose 2 or 5 choose 3 doesn't make a difference, because they end up just, in both cases, you're doing 5 factorial, 3 factorial, 2 factorial, and in this case, it would be 5 factorial. I mean, it's just literally identical, right? Because these two are going to always add up to the number that's on the top. So they're equal. We don't have to worry about that. We'll just finish that little side quest. But that's why I'm sort of not bothered about this. What I am bothered by is trying to get this into a simpler format. The way to do this is, if it's n factorial, I know it's going to be n times a number that's 1 lower than n, and then a number that's 2 lower than n, and then you could keep going with 3 lower than n, 4 lower than n. I don't really know where it ends, because I don't know what the value of n is, but I can actually just represent this as n minus 2 factorial, which helpfully is going to cancel like that. So then we end up with n squared minus n over 2. That's our value for n choose 2 that we can use here to help solve the problem, basically. So we plug this in, n squared minus n over 2, 4x to the power of 3. This will cancel. You're going to have 2n squared minus 2n times x to the power of 3. Now we come back to the problem, right? So we're trying to find n. They told us that the coefficient of the x to the power of 3 term is 20n. So to me, that tells me that 2n squared minus 2n is 20n. And we're going to have to solve this. This, to me, looks like a quadratic. So I'm just going to put a wall up and come over here in like the least organized solution to a math problem ever. Now, whenever we're in a situation like this where we have n, the temptation is always just to divide by n, which I am going to do. You do want to be careful with this because you're basically destroying a solution n equals 0. If you think about factoring a quadratic that's like x squared minus x equals 0, you've basically got x and x minus 1 as solutions. If you just cancel the x, you get, like if you just cancel x out, you get x minus 1 equals 0, which is just one of the two solutions to the quadratic. So you're destroying effectively this solution, which is why you always have to be careful when you're doing that. In this case, I know it's not going to be 0. That would be a very weird binomial expansion. So I don't care. I'm just going to get rid of it. 2n minus 2 equals 20. Divide everything by 2. N minus 1 equals 10. N is 11. And that's our answer. And that's a positive integer. Also, that's another reason n can't be 0. Aside from it just being silly, not a positive integer. So there you go. N equals 11.